how to determine the pH of a weak acid solution. So our question is this: calculate pH of a 1 molar hydrofluoric acid solution. The Ka for hydrofluoric acid is 7.2 times 10 to the minus 4th. Okay, so this is the equilibrium constant for hydrofluoric acid dissociating with water. So it is the acid, Ka, acid dissociation equilibrium constant for hydrofluoric acid, 7.2 times 10 to the minus 4th. Is this value of K large or small? It's pretty small. So in terms of acid dissociation in water, this equilibrium is going to lie pretty far to the left here with this 10 to the minus 4th value for Ka. Okay, so we are looking for our unknown here is the pH. So we're looking for the hydrogen ion concentration of a 1 molar hydrofluoric acid solution. This isn't a straightforward problem because this thing doesn't completely dissociate. So we can't take the negative log of 1.0 and find the pH of this acid solution because according to this Ka, there's not very much of it dissociated. And so what we're going to need to do here is we're going to need to figure out how much of it is dissociated based upon this Ka. So what do we know? We know the Ka. Okay, now because of the small Ka, equilibrium lies which way? Left. All right, so the next thing we want to ask ourselves is, what are the major species in solution? So what do we have there? What do we have in our sample of 1 molar hydrofluoric? We have water. And what else do we have? Major. We have HF. Do we have very much hydrogen or fluoride? Not really. It's not a major species because this equilibrium lies so far to the left. Okay, this weak acid. Okay, so there we go. Here are our 2 major contributors of hydrogen ion in solution. And so now what we have to decide decide is that is this amount of water, or is water significant? Is the autoionization of water a significant contributor to the hydrogen ion concentration? Or can we say that it's negligible compared to the amount of hydrogen ion that hydrofluoric is going to be donating to the solution? So how are we going to figure that out? All right, so this is a pH problem. What is providing the H+? So what we're going to do is we're going to look at these two ionizations. So we've got HF, and this is aqueous. I'm not even going to hardly be able to see that. Going to hydrogen plus fluoride. And then we've got the autoionization of water. Okay, so which of those two is going to be contributing more hydrogen ion to the solution? Well, to get a clue, we're going to look at their Ka's, or their K values. For this, in this case, it's going to be Kw. So for HF, the Ka is equal to, what do we have? 7.2 times 10 to the minus 4th. And for water, our Kw is 1.0 times 10 to the minus 14th. All right, so the question then is that what is the dominant source of hydrogen ion in our solution? Well, according to these K values, this equilibrium lies much, much, much further left, times 10 to the minus 14th, compared to this. So we can say, right, it's this. The hydrofluoric really is the dominant producer of hydrogen ion in this solution. So we can disqualify the autoionization of water, okay? And the majority of the time, you guys, we can disqualify the autoionization of water. The point here being, we have to know what is providing the dominant source of hydrogen ion. It's a pH problem, and so we need to go through this thought process. All right, so our dominant source of hydrogen ion is going to come from the HF. So, what are we going to do here? How are we going to solve this problem? We want to find that at equilibrium. So what are we going to do? We're going to make a nice diagram and solve for hydrogen ion. Okay, so this is now an equilibrium problem, and we've done plenty of them at this point. So what is the first thing we are going to start with? We're going to start with an equilibrium expression. And our expression is going to look like this. Let's put it up here. Ka is equal to H plus So there is our acid dissociation equilibrium expression. All right, the next thing we're going to do is we're going to make an ice diagram. Okay, so initially we start out with what? One molar. How much of these do we start with initially? We assume 0. We are going to lose. We are going to gain. We are going to gain. So what do we do next? We are going to plug these things into the equilibrium expression and solve for x. What is x? X represents both the hydrogen ion concentration and the fluoride concentration at equilibrium. But this is what we want, right? Because this is a pH problem. So once we find the value of x, all we need to do is find the negative log of that value, and that will give us the pH of the solution. So let's plug this into the equilibrium expression along with, and utilize Ka. So we have 7.2, so I'm just plugging into that thing. 7.2 times 10 to the minus 4th is equal to x times x over 1.00 minus x. What is this x times x? Do you see what I see? I see the quadratic equation in my future to solve for x. And now I'm going to do something that's going to make a lot of you very, very, very nervous. I've gotten rid of the minus x. It's made my life a whole lot easier. I do not need to use the quadratic now to solve for x. Now, why on earth would it be okay for me to get rid of that x down there? Well, look at this value of k. It's small. The amount of x that we're going to lose is going to be pretty negligible. Now, not totally negligible because, okay, it's providing the hydrogen ion in solution that is going to affect the pH of this thing. But it's not going to be very much of this 1.0 molar. So, from this point on, when we've got these small values, and we're going to check it and make sure it was okay for us to do it. But if we've got these k values that are less than 1, we're going to call this x that's getting lost here, we're going to call it negligible just to make our math easier. Okay, so, and then we'll check it. All right, so if we set this thing up, right, and we solve for x, we should get a value of x that is equal to 2.7 times 10 to the minus second. Okay, now, how do I know, because I can check now to find out whether or not it was okay for me to throw out the x down here. And we do that by using the 5% rule, the 5% rule. And so we're going to check for percent dissociation. And that means how much of it has dissociated compared to the whole. And if the percent dissociation is 5% or less, we're okay to throw out the x. So I am going to say percent, how do I want to do this? Percent dissociation, and we're still not done with the problem. Okay, right now what we're doing is we're just trying to find out whether it was okay to throw out the x to avoid the quadratic. All right, so percent dissociation is going to be however much dissociated, which was 2.7, times 10 to the minus second, divided by 1.00. The part dissociated divided by the whole times 100. I don't have this written down on my paper. .7. So what that tells us is that 2.7% of this HF has dissociated. At equilibrium, 2.7% of the hydrofluoric acid is actually dissociated into hydrogen ions and fluoride ions. But what this also tells us is because this number is less than 5, it was okay for us to get rid of that minus x. Okay, so it solves two problems here. If we need to find out percent dissociation, and that's part of our question, right? Here it is. But it also validates our ability to be able to say that x is negligible in terms of here. It's definitely not negligible, though, in terms of that. Looking around for an eraser. All right, so let's go back now. So we know our value of x, and that is 2.7 times 10 to the minus second. And what is the identity of that x? We don't want to lose sight of that. So x is equal to hydrogen and fluoride at equilibrium, and that is equal to 2.7 times 10 to the minus second. Okay, but we're not looking for the hydrogen ion concentration. we are looking for the negative log of the hydrogen ion concentration. So pH is equal to the negative, or the opposite of the log, of 2.7 times 10 to the minus second. So why don't you go ahead and do that on your own calculator. And then tomorrow in class, I will check to see that you have the correct pH written down. And the other thing that I want to say here is hydrofluoric acid and all weak acids are called weak because they're weak electrolytes. They light the bulb ever so dimly. Okay, why do they light the bulb so dimly? Because in a 1 molar solution, very little is dissociated into ions that are able to conduct electricity. So that's the reason why they're weak electrolytes. Because at equilibrium, okay, they've got a very small value for K, very little of it is dissociated into ions, and so there's just not a lot of ions to conduct current to light a bulb. Okay, so weak electrolyte. All right, we're done.